afternoon, students. So far we completed magnetic field and magnetic field lines and magnetic field lines pattern and force acting on a current carrying conductor, and we studied Fleming's left hand thumb rule also, and in the last class we studied about electric motor. And today's class, let us discuss about electromagnetic induction, which is abbreviated as EMI. So they may give you the full name electromagnetic induction, or else they will give EMI. So remember this. So today's topic is electromagnetic induction. And students, listen carefully. So for what and all topics we covered under this chapter, magnetic effects, we will get a direct question. Like they will ask, write on the magnetic field lines the pattern of a diagram, or what are the characteristics when we observe these type of a pattern, or else give the direction of current or magnetic field line based on any rule, or else principle or working or construction, explain those things. They will ask directly. Only under this topic, that is EMY, we will get indirect question, or else they will twist a question only if we understood the concept, or when we understood how to solve the question which gave under this one, which was given indirectly. So we'll able to answer this. Usually they will ask 4 marks question, like 4 different 1 marks question under the one topic. For that we need to understand the concept very well. So if they ask direct question, it will be easy. If not, we should be able to answer this. Okay, so today let us try to understand. It's not complicated, it's a very simple, just we need to understand and we need to solve some different problems or questions. And electromagnetic induction. So here Michael Faraday. I hope you already know this name. So he is the Michael Faraday who gave the concept of EMI, electromagnetic induction. And remember, this scientist is also called as father of electromagnetism. What? Father of electromagnetism. So now I told 2 points. In the both 2 points, they may give you MCQ question. The first one is, they will give who discovered the concept of EMI, and they will give 4 different options, in which we have Michael Faraday. And remember, also we'll have one more option, that is, in the first beginning of this chapter we discussed about one scientist, right? Who is that? Hans Ørsted. They will give his name also. But remember, Hans Ørsted is the one who discovered the link between electric current and electromagnetism. Is the only one who discovered the link between electric conductor, that is, when current pass in any conductor, magnetic field will produce. So he discovered the link between electric current and magnetism. But the one who gave the complete theory about electromagnetism was Michael Faraday, and who discovered the concept of EMI was also Michael Faraday. And in the textbook they are given a short biography or short detail about Michael Faraday. Read this, how he started interest in science, then how he became a physicist, everything in a small paragraph they are given. Read that one. Okay, now we understood about Michael Faraday and the 2 points. Now let us see what is electromagnetic induction. The definition of electromagnetic induction is, look at the definition. This is the definition of what is electromagnetic induction. When a conductor is placed in a changing magnetic field, some current is induced. Induced is nothing but created. Such current is called as induced current, and the phenomena is called as electromagnetic induction. See, this is, I wrote the short form of coil, don't get confused. and such phenomena is called as EMI. Now one more time, understand carefully this definition. When a conductor is placed in a changing magnetic field, some current is induced. So in the first part, when we place conductor with contact with moving magnetic field, that is magnetic field in a motion, that if you keep a magnet which is in motion, the magnetic field will create, and there some current will produce, and that current is called as induced current. So this is first part of the definition. Later on, and this entire phenomena is called as electromagnetic induction. By looking at this, we just read what is the statement, but we didn't understood properly, right? No. So to give or to understand the statement, Faraday explained the whole statement in two activity. So here we need to study two activity which are too easy. Just we need to understand what exactly happening there. Okay. So from the first activity, we'll understand how current will produced, and that is called as induced current. And from the second activity, we'll understand something happening in that activity, and that particular phenomena, or that particular, from that induced current something will happen, and that phenomena is called as EMI, electromagnetic induction. So to understand this definition, let us see what was that activity. So let us start with activity 1, understand. So the first activity is nothing but what Michael Faraday was trying to do under that electromagnetic induction. So before going to know that, in the last class I told about galvanometer, right? Galvanometer. See, if they ask for the 1 marks, what is the role of galvanometer? You should write in very short statement. That is nothing but it will detect the presence of current in a circuit. So what is the role of galvanometer? This device detect the current if it is present in circuit or not. That's it. And galvanometer is indicated with capital G. See, galvanometer will look like this, that device. See, in that device we have one needle which was showing towards 0, and we have some values here like 10, 20, which goes on, depends upon reading. So both the sides we have same readings. That doesn't mean this is positive and this is negative. Okay, it was not like that. And what is one more property of galvanometer? Recall, it will show the direction of current, right? So if the needle deflects towards this way, then the current is flowing in right direction. If the needle deflects in the left, that means current flowing in left direction. This is about galvanometer, which we learned in the last class, because we will use galvanometer, this device, as a main part or the main equipment in these activities. So I'll just tell what is first activity. So first, this Faraday, he took an coil. Here also we are using copper coil, that is insulated copper. So then what he did is, he took that coil and the ends of the coil he connected between galvanometer, which has a deflection. Okay, I'm not showing that one. While you're writing, just write down galvanometer and write one arrow mark, 0, something like this. This way some readings and this way some readings. Okay. So this, he took one coil which was connected to galvanometer. The terminals are connected to galvanometer. Next, what he did, he took a magnet and kept aside. So let it be north pole and this will be south pole. So what he was expecting is, when he kept a magnet next to the coil, he wanted, or he was expecting that the needle should be moved to show that there is the presence of current. But we don't have any battery right here. We don't have battery, we don't have plug key. So how will current will form here? So but he was thinking, without the connection of battery, the current will produce if we have only magnet. But here galvanometer doesn't make any deflection. What if it makes any deflection? It will show there is some current here. Okay, but nothing happened. So next what he did was, he took the same magnet and he started, see, if it kept like this with a fixed position, then it is called as in a stationary position. Okay, so next what he did, he started to move this magnet like towards the coil. Let it be A and B. As I told, we have one soft iron, something which was inserted in the coil, right? If you want to show that one also, show that one which was coiled around it. Okay, let it be A and B. What he did at the next step was, he took this magnet and he started to move towards the coil and away from the coil, towards and away, towards and away. While he was doing that, he observed the deflection was showing in galvanometer. So first what he did, he took coil and he kept a magnet near to it, no deflection. So second step, what he did, he kept the same coil and he took the magnet, he not kept it in fixed position. What he did, he started to move that magnet towards and away to the coil. While making that process towards and away, the deflection started to show in galvanometer. Once if the deflection started, that means what current is present in this coil. Remember, we don't have battery here. Without connecting to a battery, we are getting current in this circuit. So from this, our Faraday concluded his first statement from the first activity. That is, from this overall, what he stated was, he stated that it is clear from the activity that motion of a magnet is nothing but magnet is moving, right? Motion of a magnet with respect to the coil produces an induced current. So this magnet will get magnetic field lines like this, right? So these magnetic field lines link with coil. These magnetic field lines link with this coil, and what happens when they link? They will produce an induced current. Remember, just don't write current here. It's important to write induced current. Induced current will produce in the coil, and the deflection was shown here, and this is nothing but from his first activity stated will produce induced current. Now recall the definition which I wrote about EMI. So what was there? The first definition, when a conductor is placed, this is our conductor, this coil is nothing but our conductor, right? When a conductor is placed near changing magnetic field. See, when we kept a magnet here, we got same magnetic field lines, but the galvanometer doesn't show any deflection. But only when we started to move, we'll get change in magnetic field lines. When we started to move, the change in magnetic field lines happens only when the changing in magnetic field lines takes place. The induced current will produce. See, again changing in magnetic field lines is very much important. See, while evaluating your answers, there are some important words. If you return those words, then only you will get a marks. If not, if you summarize the answer in different way, you won't get a full marks. Okay, and in 1 marks question, they won't even give half marks. They will cut complete marks. Okay, here the changing is very much important. Then we will get, then that process or the current which produced in the coil is called as induced current. So as I told, we got a first answer from the first activity. So in this activity, what type of question you will arise? That is, see, when this magnet started to move towards the coil, so we have a north pole, right? What happens? We'll get a deflection. So it's moving, and we got, just imagine how I'm telling. When we got near to the or towards the coil, what happens? We got momentary deflection in the galvanometer. Then what happens if this magnet moving, if we have a cylindrical and if we have a place inside, it will start moving from this inside the coil. When that magnet comes to here, when that magnet comes to this part, that means inside the coil. When it comes to inside the coil, what happened? A magnet kept stationary in the inside. So it will be stationary, that means it just kept inside. There will no moving of this, there will no change in magnetic field lines. Only magnetic field lines will produce, but if it is at stationary, then galvanometer doesn't show any deflection. We didn't get any deflection. So when we started to withdraw away from the magnet, this is first step and this is second and this is 3. When it started going away, what happens? We'll get a deflection, but how? Opposite to the deflection what we got from the first step. That means when this north pole came here, we got deflection right side. Remember, when north pole comes to the towards the coil, any of the coil A or B, any of the sides A or B, we will get deflection towards right. And when this magnet start moving away, that means when start moving away from the coil, what we will get? Will deflection towards left side. So if we take this away, we will get deflection left side, or else if we start withdrawing from inside the magnet, it's moving away, no? When it started to move away, again we will get the left side. And this is what 3 marks question which you will get, and I have given in the homework. Try to answer that one. That is what happens when magnet into the coil and inside the coil and withdrawn away from the coil. You need to give only 3 words. Here we will get momentary deflection, that is right side. When it's going away, we will get momentary deflection, that is left side. And when it was stationary inside the coil, we will get no deflection. Now I understood. You learnt 2 marks question MCQ about Michael Faraday, and from this first activity, this is activity 1. Activity 1. From this we understood what is induced current, and we understood one complete 3 marks question. Okay, now let us move towards activity 2. Let's see what is activity 2. See here, we took one cylindrical roll where 2 coils are connected only in single cylindrical roll. So this is a cylindrical roll. The first coil, coil 1 and coil 2. See, these we have made a turns. Remember, for just writing the purpose we wrote like this, but in actual experiment these turns will be more than 50 or more than 100. Around 100 turns we'll get, that is copper loops. So both the cases in coil 1 and coil 2. In the first coil, what we did, the end terminals of a insulated copper wire is connected to battery, then it is connected to plug key. And in the coil 2, it was not connected to any battery or any plug key, it was directly connected to galvanometer. And coil 1 is called as primary coil. Primary coil, and this one is secondary coil. See, while if they ask you to write the diagram, you need to write it. See, while writing, write these coils properly. Just follow the textbook. How we will write means, we won't show the another one, we'll just write like this. Because another one is in the back side, which we don't show in the diagram. Just I wrote roughly here. So while writing, you need to show like this. No need to write 50 and all. Just write some 10. Something looks in a minimized way. Some here and some more here. Okay. So this is why. And the first coil is called as what? A primary, and the coil 2 is called as secondary coil. Now understood what happens here. So we are talking about what? Induced current. So here what happens, connection was done as it is, explain the construction. The next part is, when the current is on, that means when the electricity started to flow, Faraday observed that a deflection in a galvanometer, just a deflection started and came back to 0 when the current is on. Okay, a deflection went forward to right and it came back to neutral, that is 0. He observed that one. So he wondered here, if we use which technique the induced current will produce in coil 2. So what he did, so when the switch is on, we will observe a momentary deflection in the galvanometer. For your understanding purpose, I will just explain you with an example. See, suppose if the current is flowing, we have some amount of ampere, that is current, we have 2 ampere, that is 3 ampere. So let us take 2 ampere here, just for understanding purpose. We have 2 ampere of current here, that means from 0 to 2. So when 0 to 2, we will get so many numbers, right? From 1, 0 0.1, 0 0.2, then we'll get 1, then 1.2, 1.2, like that we'll get till 2. So when a current goes from 0 to 2, it will reach 0 to 2, what happens, we'll get different time numbers, and in each cases the magnetic field will be different. We'll get magnetic field different for 0 0.1, for 0 0.5 and for 1. So when a magnetic field will be different, what happens? Induced current will produce, which we understood from the activity 1, right? So when they just switch on the current will rises. So to some particular point, that is according to that appliance, okay? So when it was rises, there will be some changes in magnetic field and we got a deflection. So when we switch off the current, here we have till 2 ampere, right? It will decrease to 0 to switch off. Again, when it will come back to 0, it will come back like decreasing way, 1.9, 1.8, like 1.5, 0 0.5, then 0, right? So when it is decreasing also, we'll get different magnetic field. When it will increase also, we'll get different magnetic field lines. So all you want to understand from this activity is, when we switch on, there will be deflection in galvanometer. When we switch off, again there will be deflection in galvanometer. How? When we switch on, we will get a magnetic field lines here. As Hans Oster told now, when we have a current carrying conductor, we will get magnetic field lines. When these magnetic field lines link with this coil, they will produce induced current. When they will produce induced current, our galvanometer shows the deflection. That's it. That is the concept. And we understood, when we switch on also, we'll get the deflection. When we switch off, we'll get a deflection. Switch on, something like increasing and decreasing, that will happen, and we'll get a deflection. From this activity, we need to understand 3 points, okay? So first one we understood, and second one we understood. Switch on and switch off. And the third one is steady current. Steady current. That means the current has been fixed to some point and no change. We are not offing, we are not oning. What happens to this galvanometer? When we switch on, when we have a steady current, then remember, we don't see any deflection in galvanometer. That is because when they are fixed current, we'll get only one type of magnetic field. Only when the current is moving up and down, the magnetic field will keeps on changing. When it is fixed, magnetic field lines also fixed. When there is no change in magnetic field lines, then there will be no induced current. We understood, right? Motion of magnet only gives rise to different magnetic field lines. Only when the different magnetic field lines create, that means when the change in magnetic field lines is there, then only we will get induced current. So from this we understood, when we'll have a steady current, then we'll have a steady magnetic field lines. They will be moving with the same property. There is no change in steady current, there will be no change in magnetic field, hence there is no induced current and there is no deflection. This is what activity 2 suggests us. But the process of the second activity, that means how the galvanometer shows the deflection, that process is called as EMI, electromagnetic induction. So what happens when a current passed in this coil, magnetic field lines will produce and there will be change in magnetic field lines, and this will link with this coil, and again this we observe a different magnetic field properties, and it will produce induced current. So from the primary coil, that is coil 1 is called as primary coil, right? From primary coil, induced current will produce in secondary coil. The details no need to write. The details is change in magnetic field and change in current, something like that. If you don't, just try to understand, no need to write that in your answer. The induced current will produce in secondary coil from the primary coil, and this phenomena is nothing but electromagnetic induction. So now we understood both what is induced current from activity 1 and what is this is what electromagnetic induction from the secondary current. This is what we need to learn from this chapter, from this under the topic. We understood only activity 1 and activity 2, right? So from here again I will continue in Wednesday's class. So while starting the Wednesday's class, try to recall what and all we learned in today's class. Answer the homework question. Only few homework question I will give. Write on the notes and understand the concept, what happens, okay? Thank you. One question, an in-text question. Explain different ways to induce current in a coil. So how to produce induced current. So one we understood, if you took a magnet, I wrote the diagram, if you took a magnet next to coil, if you keep moving that magnet, the induced current will produce. That is one point. In the question they told different ways. Then what will be our next possible way to produce induced current? That is nothing but, in the last class we learned about horseshoe magnet, right? It will be like this. So if we kept a coil in between this horseshoe magnet, and if we keep on moving this coil, means that particular coil, if we keep on moving that particular coil, then the induced current will also produce through horseshoe magnet. One is natural bar magnet, another one is from horseshoe magnet. And we have 14th exercise question which are given in the homework, which is similar to this situation. So try to think and try to answer the 13th question. See, these are hints. So you should think and answer the question. See, I know you have some apps. You will get a direct answers for all exercise and in-text questions. Even though if you copy those answers, first understand what is the situation, then think whether that answer is correctly matching your question. Just analyze and write the answers.